Welcome to this video. We're going to begin option A. This is sight, the eye, and wave phenomena. So first we're going to look at the structure of the eye. This is the basic view. We're looking at the eye here from the side. Now the left side is where light enters, and the right side is the back of the eye. This is the front on the left. So light enters through the front of the eye. It can come sometimes at an angle. It's bent. It passes through all of this structure, and it strikes the back wall. When the light strikes the back wall, something special happens. An electrical signal, or impulse, as we call it, is sent through some optic fibers to this optic nerve. Where it's received, it goes all the way to the brain, and then the brain processes the information, and it creates the perception of vision. It creates vision or perception of objects. So the first thing to look at is this special back wall called the retina. This is where the magic happens. The retina is a light-sensitive layer, and what we mean is it takes the incident light and it converts it into electrical impulses that the brain then processes. The way this happens is through things that are called rods and cones. So here's a zoomed-in view of the retina. You have all of these little rods and cones kind of sitting at the top, and then there are these little optic fibers coming out the front. This is kind of a backwards picture. People often say that the cones and rods are backwards. And the reason is because light coming in it has to pass kind of through or beyond these fibers, and then it can hit the cones and rods and stimulate them. So all of these little fibers are running across the surface, the outer surface. Light passes by them when it strikes the cones and rods. They all combine together over here, and that is called the optic nerve. So each cone and rod has a tiny little nerve fiber, and all of those fibers connect together at the optic nerve. And the optic nerve is what carries those electrical impulses to the brain. Because the optic nerve because all of those little fibers have to go from the outer layer down inside, so it has to pass through the retina, there's a hole in the retinal surface where all of those optical fibers come together, where the optic nerve passes. That hole is called the blind spot. You don't have any cones or rods on that surface, and so you can't see any light striking the surface. That's what the blind spot is. There's kind of the opposite of the blind spot. The blind spot is this area where we can't see because there are no cones, no rods, no photoreceptors. There's also a fovea, which is kind of right along this dotted line, right behind the main center point of the eye. So if you trace this line all the way back, that's called the principal axis. You hit the fovea. The fovea is a position on the retina where the cones are at a maximum and our vision is really, really sharp, very acute at this one position. In addition, we also have something on the outer layer called the cornea. The cornea is a layer of transparent skin. It refracts light toward the fovea, and it helps to focus the images. So when light comes in, it's partially bent by the cornea. There's also the lens, which is the real powerhouse. That's the main component for focusing light. So the lens does most of the focusing, and the lens is dynamic. It can take on different shapes. It can be thick, it can be thin, and we're going to make an analogy here to glasses. When we joke about, old people glasses, we say they're extremely thick. Cartoons often portray this. Really thick glasses, they are powerful because they bend light so much. And likewise, the thicker the lens, the more the light will be bent. A thin lens bends light less. In addition, there's this iris, which kind of covers up. It's sort of the pathway, it blocks or allows light into the eye. The iris is a ring, specifically, it's a ring of muscle fibers. Sometimes you get some cool colors on the iris, but the iris is what we refer to when you say, what color is your eye? The iris relaxes and contracts. When it's relaxed, it's thin. It's not a it's not a thick ring, it's just a very thin outer ring. And in that case, there's lots of light entering. When the iris is contracted, it's thicker, it expands, just like when you flex your muscles get bigger. So that ring gets bigger and it blocks more light. So if it's nighttime, your iris relaxes to allow more light in. If it's bright at noon, then your iris contracts to block more light. There's also these things called the humors. The aqueous humor is in the front and the vitreous humor. And these are the transparent jellies. They have nutrients or they have things in them that nourish the eye, but they also help to keep the eye's shape. So they're not, this is not empty space here. There's some transparent jelly-like substance called the humor. Now, the eye is capable of looking far away and looking close up. Close vision requires a thicker lens. When we are looking as close as possible, we call that point the near point. It's the closest the human eye can focus, and it's about 25 centimeters. We also have distant vision, and if we look, here's a thick lens. By comparison, that's a thin lens. The lens is thinner, the far point is the farthest we can focus, and it's so far compared to 25 centimeters, we might as well take it to be infinity. And the cool thing is we said that thick glasses bend light more, and thin glasses bend light less. We can see that that's true from the picture. Light is coming at this quite large angle. It's coming, at this angle, and it's bent all the way back. Whereas here, it's coming straight ahead, and it has less bend. Here, we're bending more, where it's almost like we're bouncing off, and here we're just being bent in a little bit. So the last question we're going to look at in this video, and this will take a couple of slides here, but how does this process work? How does the lens change shape? Okay. Because the lens itself is just, it's just this clear material. It can't change its own shape. Something must control it. The thing that controls the lens is the ciliary muscles, which are connected to the fibers. The ciliary muscle is this outer, it's kind of like the iris. It's an outer ring that encircles the lens. And because it's a muscle, it flexes and contracts. That muscle, as it flexes and contracts, controls the shape of the lens. The way this works is there are fibers connecting the two together. So the contraction and flexing of the muscle via the fibers changes the shape and thickness of the lens. So let's see how that works. Here's, let's say this is the lens on the inside. On the outside here, we have our ciliary muscle. It's a ring that encircles the lens. And then we have the fibers here. This is what it looks like when relaxed. Relaxed means you're not flexing, your muscles aren't very big. So the ring is kind of, I'm sorry, this is contracted. This is contracted. So we're flexing, this ring is thick, and as a result, there's not a lot of tension right here. It's like the string has been loosened. On the other hand, if we relax those muscles, then we're not flexing anymore, and the ring gets thinner, and it pulls the fibers in, or out, I should say, and as a result, this lens flattens. It gets flatter and thinner. So ciliary muscles make a thin ring over here, a thin ring when they're relaxed, and then when you flex your muscles, the muscle gets thicker, just like when you flex your arm, your bicep. And as a result, we loosen the tension in these little strings, these fibers, and it allows this thing to kind of relax and kind of squish up a little bit. So that process is called accommodation, and this flexing and relaxing is what allows the eye